My name is Bob, for those of you who don't know me. Since August, I have been the director of the UCL-Energy estate. Looking forward to doing all sorts of damage in this place. We'll see how we go. It is my enormous pleasure this evening to have to introduce Phill Biddulph and Elwell. A few words of introduction for both of them. Phil's career spans astrophysics, particle physics, and building physics, from the unbelievably big to the unbelievably small and going round and round in circles, to the useful, somewhere in between. I think you've done really well. Apparently, he spent several years at Manchester University where he invented Brian Cox. I don't know if that's true. We should probably check. His CV also records several years spent at CERN and several more years running a research group in Cambridge. We are delighted to have him here. Their loss is very definitely our day. Cliff Elwell studied natural sciences at Cambridge, which didn't do me any harm, and doesn't appear to have done him any harm. He then spent nearly 10 years in academic publishing. A little bit less.
5 years postdocing making computer memory.
That was it. 5 years making computer memory, and then some time in academic publishing. So we have a number of students here, actually. If you find that Cliff is sometimes amazingly keen to get you to publish, it is because that is what he did for a living, trying to get recalcitrant academics to actually put their thoughts down into paper so that they can be published. He then joined the Energy Institute as the academic manager for the low Centre for Doctoral Training in Energy Demand Reduction. And once again, it was our game. It's remarkable, and a comment at least as much on their abilities as on the state of UK building science. Having arrived at UCL and having linked up with each other, they decided to try to revolutionise the study of energy use in buildings by systematically applying Bayesian techniques. Their first joint paper contains the biggest number in any paper on building science that I've ever seen. I urge you to keep an eye out for it. So in just a couple of minutes, I will ask them to come forward and begin their talk. I just need to run through a few items of housekeeping first. First of all, the fire escapes. The fire escape is out to the back of the room, down the street. If for any reason that route is blocked, then there are other routes in the opposite direction through the building, but that's unknown. I will ask Phill and Cliff to speak for about 45 minutes. I will stop them at 45 minutes because I would like to take questions. I suspect that a number of you will have questions. And we're ready now to take questions. Following questions, we would like to, the Energy Institute would like to invite you upstairs to our kitchen to join us for some refreshments. This is the way we normally end seminars here at the Energy Institute. It would be lovely to have you there if you can stay. And volunteers for the evening should be at the back of the room and advise. Yes. And if you do leave after, is it 7:30 or 7 o'clock? 7 o'clock, yes. If you should want to leave the reception upstairs after 7 o'clock, then you will need to find a member of UCL staff or a student to accompany you out through the door. So the doors have to be opened using the key cards that those people possess. So there are people at the back of the room who will wave. They wave. Nobody ever finds it difficult to find a number of UCL staff across the single. Okay, that is by way of introduction. I'd now like to ask Phill, I think, to begin proceeding.
Hello, everybody. So this is an outline of what we're going to talk about. I'm going to introduce a little bit of Bayes. I'm going to talk about whirls, and then hopefully, if I leave any time at all, Phill will talk about boilers. When we first thought up the title for this talk, I put Bayes in because that's the method we were using to do the analysis. But then I got quite a lot of emails back saying, please can you introduce Bayes to people because everybody struggles with it. And that sort of changed the nature of the talk. So I thought, yeah, okay, but how can I do that? What's the best way to explain Bayes to a general audience? And it's actually very difficult. Bayes is an enormous subject, and to describe it in a few minutes is not easy, but I'll give it a go. Even physicists find Bayesian analysis difficult to understand. It's sometimes find it difficult to understand. There's a bit of a threshold. Once you get above this threshold, it all becomes very easy, but it's just getting your head around the way it works. So I would class myself as before as being statistically challenged. Now I think I've got some idea of how it works. If you drill down to the bottom of it all, the fundamental difference, or the fundamental new thing, is probability. It's the understanding of what probability means. In the sort of frequency definition, it's the long-running relative frequency with which an event occurred given many repeated trials. It's just there. In the Bayesian view, probability represents the state of our knowledge, what we understand about something. So to try and illustrate that, I brought along the box. Okay, it's got something in it, which is rigid, and we've got to think how long is the something in the box. To do the analysis, we've got to think about probability distributions right from the start of the analysis. And remember, these represent our understanding, and they can change as we do the analysis, so it's not a fixed thing. What can we say about the box, whatever is in the box? It's, we can set the range. We know the minimum size. It can't be less than 0 length, whatever is in the box. And it can't be greater than the maximum length, which is determined by the width squared times the height squared times the depth squared. So it's this angle here, this length here. So we can express that information as a plot of probability density, which is flat, which says that between the maximum length and the minimum length, everything is possible. It's all equally probable that we'll get something like that. That's the state of our knowledge about what's in that box. Okay? Now, I'm not saying this is in the box, but imagine you know about carrots. What do we know about carrots? They're orange. They help you see in the dark, apparently. And my kids like to eat them raw. It's a good tip, by the way. But how long would you say a carrot is? Let's get my props out before we started. So I've got a ruler here, which will come in useful a little bit later on. But roughly, carrots can be anywhere between sort of this length and that length. But you could, how would you express what you know about carrots? You can draw a distribution, which describes our knowledge. They can't be less than 0, and there's a sort of an intermediate length where if you were said how long is a carrot, you would say maybe 20 centimetres or something like that. It would be a more likely length, but you would be surprised if the length of a carrot, say I just plucked out of the air, was bigger than, say, a metre or something like that. Now I can go into a sermon about data quality and how you measure carrots. Do you measure it from the tip to the end of the green bit? Or do you measure from the tip to this bit? Or do you measure the length along here? And so on. But we won't go into those problems today. We're just measuring the carrot from the tip to the boundary with the green bit. So this is the most likely length of carrot, and there's a low but not 0 probability for large carrots. So how long is the carrot in the box? And this turns out to be very easy. All you do take the first distribution, prior knowledge, new data, which is the estimate of what we think is in the box, multiply these together bit by bit as you go along, and you get a new distribution. I'll use this red thing here, which is here, which has no carrots longer than the box. Okay? And we normalise this so that the probability of finding a carrot of any length has got to be between 0 and the maximum length of the box. And the most likely length of carrot is that length. Okay, so there's our carrot. And I can measure the carrot now with my ruler, and I get roughly 11 centimetres. Which is a reasonably accurate measurement. So when I do that, I take our prior knowledge. Remember, this is the truncated distribution we had before. The new measurement, which was, what was it, 11 centimetres, with a plus or minus 1 centimetre uncertainty, but it's a reasonably accurate method. You multiply the prior by the new data, and you get a new belief. And you can see that the prior data has not really influenced the new measurement too much, but it's fixed the boundaries. So I could ask somebody else to measure the carrot, and perhaps they get a new value, which is, instead of 11 centimetres, is 1 centimetre, because they're much more careful at measuring it, or they use a different ruler. And we can take the prior knowledge, new data, and get a new length of the carrot. So I'm using words here: prior knowledge, new data, and posterior after belief. So this distribution says what we believe, can we believe the carrot, the length of the carrot. Now, if I take my glasses off, I can't see a thing. And I measure the carrot again. Could be, I don't know, 15 centimetres, something like that. As you can imagine, the uncertainty now in that length of measurement of the carrot is much bigger. So this is the new data here. Let's just see. New data, I've measured it roughly 15 centimetres, but I've got a much bigger error on that measurement. So I take the prior knowledge, new data, and combine them together, and I've moved the carrot length a little bit with this new data, but not much, because the uncertainty in how well I measure that measurement is not good. So this is quite easy applying Bayesian analysis. You can take old data, new data, combine them together, it's quite easy. The problem starts to happen, or the hard bit of Bayesian analysis, is when you get this in more than one dimension. And we've got models with 14 dimensions, and you're trying to find the peak in 14 dimensions. And that's where things like Monte Carlo techniques come in, and so on. So that's a very brief introduction to the idea of probability distributions and how we use them to express our belief in something. Oops, wrong one. So now we come on to the physics bit. Whirls. So measuring the thermal resistance of a wall, we need a wall, warm air, heat is going through the wall towards the cold air. We need wall, thermometers, and a heat flux meters to instrument this wall. And fortunately, upstairs, we may be able to see it later on, there is a wall that we've removed the insulation from in one of the offices for the students. We've taken the insulation away and put heat flux sensors on the wall and thermometers to measure the internal surface temperature, and also on the outside of the wall. This is Virginia, who's done all the work on this. If you just take the parameters of the wall and look in a textbook, you can calculate a U value of roughly 1.82 for this particular wall. And when you look outside with the thermal camera, you can actually see the space here where the insulation has been taken off. You see that's a little bit warmer. So this here is a window. We've got flux sensors on the thermometers on the window sill here, and on the outside wall, and on the inside wall. So just to show you. Okay, yes. So this is a movie of the data as it's coming in. This is temperature here, so it's color coded. This is the wall, and this is the window. So this is inside, and this is outside. The dots here represent thermometers, and the colours of those represent the temperature they're reading at this particular time. This is in July last year. The bars here are the measured heat flux going into and out of the wall. So just at this time here, evening, early evening, there's large amounts of heat leaving the wall, the wall's cooling down, there's nothing much happening on the inside, and as the sun comes up, the inside gets warmer, more heat is going inside, and so on. This yellow blob here that's moving around is actually a representation of the sun, because we know the time, we can tell where the sun is, and the size of this dot tells us how much sunlight is actually coming to this, how much light there is at this point here. So when it gets big, that means it's gone past a cloud and shone directly on the wall. So you can see the data coming in. What we've done is looked at just one of these flux meters. Yeah, I think that's enough. We just looked at one of the flux meters and the thermometers from this side of the wall and that side of the wall to investigate what's going on in the wall, how the heat is moving through. So to do that, we can't just take the thermometer data, the temperature data, and the heat flux data. We need some way of converting that into things we can use Bayesian analysis for. So instead of direct measurements of something, we need something called a likelihood function, or a model that tells us how to interpret the data. So the likelihood function produces a probability distribution over the parameters of the model. So in a model, and in the model it has a parameter, and we need to vary that parameter and see how the data, how well that model works with the data. So another way to say it is the likelihood is the probability of the data given a set of model parameters. Now, this is Bayes' equation, and it's daunting when you first see it. Each of these bits have got names. This is called the posterior, this is called the likelihood, this is the prior, this is the prior information, this is the likelihood information or data as we had before, and this bit here, the evidence, is a normalizing factor. But perhaps an easier way to sort of understand it is to try and understand this cartoon. So to read this, you read the probability, so this P means the probability of something given something else. So the probability I'm near the ocean, given that I picked up a seashell, is equal to the probability I picked up a seashell, given that I'm near the ocean, multiplied by the probability I'm near the ocean, divided by the probability I picked up a seashell. And the idea behind this is, if you picked up a seashell, you're probably near the ocean. Okay? So statistically speaking, if you pick up a seashell and don't put it to your ear, you can probably hear the ocean because you are near the ocean because you picked up a seashell. Get that? Does that make some sort of sense? So we need a model now for our wall of how heat is moving through that wall. And the simplest one is a single thermal resistance. So we assume the wall has no mass, and that as soon as the temperature changes, the heat flux changes in the wall. We have an internal thermometer, a heat flux meter, a resistance, and an external surface temperature thermometer. And our model is that the heat going into the wall at this point here, Q, is equal to the difference in temperature divided by the thermal resistance. So this model only has one parameter, R, and we need to find a peak in a one-dimensional posterior probability distribution. So if we go back to the plots we had before, for this particular model, I've used a non-informative prior. That means the prior is flat. I think the resistance is somewhere between 0 and 3 meter squared Kelvin per watt. And so that's my prior. It's nice and flat. It's easy to do the maths. And then I need some way of calculating the likelihood and how well what the probability of the data given particular value of R is, and this is proportional to this chi-squared calculation here, where the Q model is given by a model from the temperatures and the resistance, where we scan over this R value, and the data is the data that we've collected. And it turns out there's an incredibly narrow peak here at this value when we run this. So the thermal resistance is 0.407 plus or minus 0.001, which is quite an accurate measure of that. This then gives us the posterior, and we can see that's dominated by the good quality data. The trouble is, when you run the model with different temperatures, if you got the data is the red line here, and the blue is the model run with the temperature decisions going along, it's not a very good model of how the heat is going into the wall at all. So the heat is not going into the wall like this. On average, it's right, but instantaneously, it's not working at all. So we need a more advanced model for the wall, and this is one. It's the next most complicated one. We introduce thermal mass. So we're using electrical analogy here, so the thermal mass is equivalent to a capacitor in a resistant RC circuit. We have the internal temperature. So now we have 4 parameters, which are the resistance from the internal temperature to the thermal mass, from the thermal mass to the external temperature, the thermal mass itself, which is an effective thermal mass. It's the mass associated with this heat going on this side, and also the initial temperature of the thermal mass. These 4 parameters are what go into our model. So we need prior distributions, which we use non-informative ones, and then we need to find the peak in a 4-dimensional posterior distribution. So that's when things like Monte Carlo techniques come in, where you hunt around for that. So using this, we get, for the single thermal mass, we have the 4 parameters, we find the peak in the distribution, and we find these resistances, this thermal mass, this initial temperature of the thermal mass, and the total resistance now comes out at roughly 0.4 meter squared Kelvin per watt. And you can convert that to a U value. So what we get then is a very much improved prediction of the heat flux into the wall. So this is the red is the data, and you can see now we really are able to predict roughly on a 5-minute by 5-minute basis how the heat moves into the wall. There's some discrepancies here and there, but it's not bad compared to the other model. Right, so we've eyeballed these 2 predictions, the heat going in using the single thermal resistance model and the heat going in using the single thermal mass model. But Bayesian analysis allows you to take these 2 predictions, 2 models, and work out which of the models is best. And you have to look at the ratio of the probability distribution, posterior probability distributions. So that's the probability of the model single thermal mass given the data, divided by the probability of the single thermal resistance model given the data, equals Bob's fantastic number, which is enormous, which just says that it's there has to be a thermal mass in the wall. It doesn't work otherwise. This method, which I can't go into detail because that's a whole lecture course in itself, is much better because it takes account the size of the priors. If you have 2 big priors, it penalises you for that. If the number takes account of the number of parameters, so too many parameters, it penalises that. And it also takes into account how well the models describe the data. So, because the model has 3 different bits to it, it has the heat going in here, the thermal mass, and the heat going out here, we can actually predict the evolution of the thermal mass temperature, which is this black line here. So you see it's closely following the internal temperature, and which is hardly surprising because this thermal resistance here is quite small, so it's following that. The other advantage of this method is because we're taking away the thermal mass the calculations really quickly, we get a much faster analysis. So this x-axis here is the date, or the amount of data used to calculate the U value at that point. So here we use roughly 3 days worth of data to calculate the U value. This line here says that in the previous 24 hours, the U value hasn't changed by more than 1%. So the single thermal mass model has already, after 3 days, got the U value. Whereas using the single thermal resistance model, it takes roughly 7 days before it converges. So that's the thermal mass working its way in the system, and because you're taking more and more data, the effects of it get less and less. Just for comparison, here is the calculated one, which in this case is quite close to the ones we got from measurements. Just as a bit of a teaser, we can also look at how the heat flowing out of the wall into the outside is working. And this is given by, so the red is data. We've actually got heat flux meters on the outside of the wall, and the blue is the model. And as you can see, the model's not doing too bad, but there are lots of spikes on here which we're going to have to investigate to understand why that's happening. Okay, I think I'll hand on to Phill. Did I leave you any time?
Yes. Plenty. So I'm listening.
Great, so Phil's done the easy bit. We've done a little bit of an introduction to Bayes, and we've done 4 dimensions. We're now going to push all the way up to 14 dimensions. Excuse me, I've got a bit of a cough. And we're going to be looking at UK domestic gas demand and its relation to a policy that was introduced in 2005 to make all newly fitted boilers condensing. With the question, can we associate any energy savings with this, and what kind of size might those be between currently saved and perhaps projected savings? So I'm going to talk a little bit about the data that we've used to do this, and then introduce the models very briefly. And there are 2 parts there, the way that the boilers increase in the stock, and of course physical models of gas demand, and then we'll go through the results. So this is the data. We've used national data sets to do this. And you can see here at the top, this is gas demand, this is external temperature per quarter, and you can see that roughly when the external temperature is high, gas demand is low. And at the bottom we've got retail gas price index. Now, whilst you can see this link between these two, you can't see a subtlety here of the impact of the price impact. So we certainly need to apply some statistics here and much more to work out what impact efficiency might be having on this, given that I'm saying there was a change in regulation here. What else have we used? Well, we've used boiler uptake statistics, number of dwellings in the stock, the number of boilers, and then the number of condensing boilers. In 2005, is that there somewhere? The new regulation came in, all new boilers have to be condensing. That's great because we've got a fixed point in time, which allows us to apply different rates before and after the introduction of regulation. So that's a really great way to get the analysis started. So I'm going to give us an overview of the way that we've done the modelling here. We've used models that are dependent upon quite a small number of factors, so external temperature, gas price, number of boilers, number of condensing boilers. And I'm going to give you a very abridged version with most of the maths removed. Anybody wants any more maths, we'll happily talk maths later. So uptake dynamics. If we think back to the graph of the number of boilers and the number of dwellings and so on, and you think about how this might work, you can see that there's a population of dwellings and a population of boilers and a population of condensing boilers. The population of boilers is limited by the number of dwellings, and the number of condensing boilers is limited by the number of boilers. This sounds an awful lot like population statistics, for which we use the logistic equation in ecology or biology, and it's also used for technological update models. It produces characteristic S-shaped curves. Now what we're going to do here is, well, let me talk you through it first. Logistic equation, the rate of change of the number of boilers with time is a rate of increase of number of boilers in the stock, 1 minus number of boilers over the total population here. So this is kind of a scaling factor. The complex thing here is that we've got the number of dwellings. Now we're going to increase that linearly in line with government projections. But then the number of boilers in the stock, well, that needs to have this applied because we've got a population limit that we have to put on. And then the number of condensing boilers, well, that's applied too, but that's a secondary logistic equation on the data produced by the first logistic equation because you're limited now by the number of boilers in the stock. And of course, we've got different equations for before the introduction of legislation and after the introduction of legislation. So I'm going to skip the maths and summarise that we now have 7 parameters associated with this part of it. That's the number of dwellings before, at the start, the number of dwellings with boilers, and the number of dwellings with condensing boilers, and the rates of increase associated with each. And then we need one more thing, we need the rate of increase of condensing boilers after the introduction of legislation. We've got data for the rest. So this isn't too bad so far, and we've identified a little bit there. I'm going to glaze over the fact that this is the number of boilers in the UK and the data's for England, so we have to scale that, and some of the issues with what we do over efficiency, which we might see later. And now we're going to focus on this second part, where the energy use is fairly obviously directly proportional to the number of boilers in the system, the efficiency of those boilers on average, and then the demand, which we've broken down purely into what we're calling space heating and water heating. And we'll see later a different temperature dependence of those two. And we've arbitrarily called them space and water in line with our expectations of the dominant demands for those two regimes. So we're going to present just 4 models today, although we've looked at many more. The first one is the simplest model. And there's a temperature dependence of space heating, which is here. And there is, but water heating is independent of temperature. And then we've got a factor here, a gas use, which is dependent upon price. We haven't related that to water or space heating. So it's kind of slightly strangely outside the equation just for now. It's worth bringing in this balance temperature here. The balance temperature, is this temperature here. It's the temperature above which, the external temperature above which you don't need the heating on to meet the desired internal temperature. Because your free heat from people and from appliances and from solar gains is equal to, gives you the right temperature rise to achieve thermal comfort. Or at least the chosen thermal comfort. People aren't necessarily comfortable. And then this linear increase of energy use with price is there. Model 2 is just the same as Model 1, but now what we're doing is we're saying, well, let's just make water heating completely constant. We'll get rid of this funny factor outside, which is a price dependence, and now we're going to make the set point, effectively, for the space heating to be dependent upon price. So, but the way that we've done that is now that this balance temperature is dependent upon price. And other than that, it's the same. It's got the same number of parameters, 12 parameters, and it substitutes into the same equation. Model 3, a little bit more complicated, 1 more parameter. So now we've got the 7 original ones and 6 new ones. Now we've got exactly the same balance temperatures, but we decided to include a separate price dependence of water heating. So perhaps people use water slightly differently from the way they use space heating in relation to the cost of energy. And that's reflected in this graph here, where you've got 2 different price dependencies of gas use on price, and they sum to give an overall one, which is a kind of a merging of many different factors on it. The final model is, of course, the most complicated, 14 parameters. But all we're doing here is including, incorporating a temperature dependence of water heating. We could do lots of other models, and indeed we did look at lots of other models, but we've tried to reduce it to 4 that are vaguely physically sensible and produce reasonable results. We could just get rid of the plateau. We could have a secondary plateau in external temperature and energy use. This would indicate people's heating not meeting demand and being limited by system size not meeting demand or something like that. Or we could decide that every season is going to have a slightly different relationship, and that might indicate something to do with the thermal storage of the system, the weather in different seasons and things like that. Because of course the balance temperature, don't forget, incorporates solar radiation and so on as well, and that changes from season to season. So perhaps that's different as well. But we ran a model comparison to work out how these compared, exactly the same way as Phill showed you earlier. I've been slightly lazy, and instead of giving you all 12 different permutations possible given these models, I've just normalised them compared to model 1. And we can see that this model 2 is slightly more physically plausible, where we brought the temperature dependence within the equation on space heating. But model 3 is much more plausible, where there is a temperature dependence of space heating, separate price dependencies of space and water heating. But water heating in this model is independent of temperature, in here it's dependent on temperature. This says that model 3 wins. And now we're going to use model 3 for the rest of the analysis. So the model churns out lots of things that you can interpret in different ways, some of which might be interesting, and these are the headline figures. As you would expect, the rate of condensing boiler fitting goes up by a factor of 4 after you force people to install condensing boilers instead of regular boilers. There is an exception to the rule sometimes. We've neglected those. The number of boilers fitted after that date meeting the exceptions is very low. We've calculated the specific power loss per property, 215 plus or minus 10 watts per degree Celsius. That's quite a useful figure if you want to get an idea of the impact of temperature on energy use and the performance of buildings in the stock. One thing to be aware of with this figure, though, is that we can't calculate this for every year. We can't see it evolving because there are simply too many parameters if we allow that to change. We've got more parameters than we have data. So what we've had to do is that's an average for the whole time. And you might expect in that time period, 15 years, that the performance of the dwelling structure has improved through more double glazing, more insulation, things like that. We just had to neglect that. It's all bundled into the error instead. And the balance temperature here, which again is only dependent upon price, has gone down by a degree Celsius, and gas prices have gone up an awful lot at that time. How does it do? Well, here we've plotted the crosses in the model, and the error is all being put onto the data for a simple way of doing it. And this is external temperature and gas use. Now we've got our data is for the number of dwellings, the number of boilers, the number of condensing boilers, and the price as well. So we've only got one axis here, so of course it's not in a straight line. But we can say that the fit is very good. These error bars are supposed to be 67% error bars. They're actually a slight overestimate because we've used a simplified model to estimate the error. And you see that far more than 67% of the data falls, the model estimates fall within the error bars on the data. So it's performing really well compared to our expectation. Do it slightly differently. Slightly more useful plot, perhaps. This one is external temperature running along the bottom, but now we're seeing how this evolves over time. And what we see is, I think there are two key features here. Firstly, now this is the gas use per boiler, and we're seeing a decrease over time. So the people are using less gas per dwelling, per boiler over time. Secondly, the size of this plateau is increasing. That's the balance temperature going down. So let's think a little bit more about this drop here in use. That must be telling us something about efficiency, as well as price, because remember price still isn't on here, and price has gone up enormously in that time period. So let's just look at efficiency for now. So we've managed to isolate efficiency. And here I actually introduced this slightly convoluted factor, which is how we've had to account for efficiency, because we need to see in the data it's too many multiples of different efficiencies means you can't resolve them. So we've had to introduce a factor as a 1 plus for clarity, or for clarity to actually be able to do the analysis. So the efficiency of a condensing boiler is equal to the efficiency of a non-condensing boiler multiplied by 1 plus a factor, an increase in efficiency factor. This increase in efficiency factor is 0.25 plus or minus 0.15. That means that if we assume that regular boilers have an efficiency of 72%, which is what SAP says, the standard assessment protocol, it's kind of a standard value to use, then that means that condensing boilers would have, according to this data, have an efficiency of 90% plus or minus 10%. It's about right. Condensing boilers have that kind of performance. It really critically depends on what you think that initial starting value should be, and that's a scaling factor. If I just whiz us back a few slides. The great advantage to these models is that these are just scaling factors. So if we come up with a better, because we've set it up with the efficiency of non-condensing times 1 plus factor gamma, this means if we come up with a better estimate of the efficiency of non-condensing boilers, and we found it very difficult to pin down an estimate of what the real efficiency of non-condensing boilers in the stock is. But if we do come up with one, we can just substitute it, and it's a linear, it's an inverse relationship, so it's really simple. You can just scale all the results very quickly. And it gives us some energy savings, and the energy savings are reasonable, perhaps. 176 gigawatt hours over the 8 years that we analysed, when the total use is 360,000 gigawatt hours per year. So it's a reasonable amount, and this is what it looks like in terms of the evolving efficiency of the stock. Now, this is the number of the total gas use. Well, the number of houses is going up there, and the number of boilers is going up as well. New boilers aren't fitted just because new houses are built. Some houses have central heating installed for the first time. And here, we find that on a per boiler basis, it's going down pretty consistently throughout. After the introduction of the legislation, it accelerates, but price goes up. But what we can see here is that our projected change in the efficiency of boilers in the stock is fairly smoothly going up. This is the average efficiency of the whole boiler efficiency of the whole stock, which we assume starts at 72. So now we're in a position where we can look forwards and work out how much energy might be saved in the future. So we could say, well, let's see if we introduce this legislation at different times. We took a bunch of years, 2005, 10, and so on, and not at all before 2050. Let's assume what we're trying to do is save as much carbon as we can between now and 2050, by which time hopefully we've saved in the region of 80%, in line with government targets. And let's see what the energy and carbon savings are. Well, the good thing is that we set up the logistic equation. So whilst obviously the uncertainty estimates get far, far bigger the further away you get from your data, but you can still project forward because you set those forwards. You set those up to be a long-term relationship rather than simple linear regression or something like that, which simply wouldn't let you go very far away from your data. And here we see the model estimating the number of dwellings. That's linear. A logistic equation here for the number of boilers, and then we're looking at different times of introduction of the legislation, and then no regulation at all at the end. Well, how much carbon might that save? A fair amount. I mean, it depends on what you think a large amount of carbon is, I suppose. And it's also worth noting that we've assumed that this technology is not wiped away. We've achieved a technology vacuum. Heat pumps don't come in and wipe all this out. Condensing boilers don't come in anyway. We've had to assume status quo in terms of technology and policy. So, but in that light, we see a 2 million gigawatt hour saving, which is about 5.6 times UK annual gas demand. It's a reasonable amount over about 45 years. That's from the full introduction in 2005 to the end. We see the effect of introducing the legislation at different times. Big error bars on this because it's projecting forwards, and all the error ends up coming into projecting forward on every parameter. You start to see error looking much bigger there. And this is projecting right out to 2050, so huge error bars here. But we see that it's fairly linear at the start. About 60,000 gigawatts hour a year in the early years saved by introducing the legislation. And the message is pretty simple, and in many ways pretty obvious. If you want to save energy through legislation, introduce carbon or energy through legislation, you've got to introduce it as early as you can. And then in later years, you can see that the tails of the logistic equation start to come into play, and it becomes non-linear. So what we tried to do today is bring you through the kind of analysis that we normally do using two examples. And partly why we've run through the examples very quickly is we wanted to show you a couple of ways that you can apply these techniques. And it's taking very simple physical models, as simple as we can, whilst being sensible, and trying multiple models, trying lots of them, and then comparing the data evidence for each. And then undertaking a Bayesian analysis to try and extract useful parameters, and such as the U values of walls, or the heat capacity of walls, and the energy savings associated with policies. And you can apply this all over the place with the right data. And bearing in mind that in the second example, we had a fixed point in time when new legislation was introduced, which allows us a known date of rate change, which is wonderful. Very rarely do you have that kind of fixed point in time. And we're always limited by data quality, unfortunately, as is any statistics. Thank you.
Well, some questions. Okay, fantastic. Could you give your name and your affiliation, please? Just so.
My name is Phill. I'm from Columbus School of Hygiene and Tropical Medicine. Thanks very much for a very good talk. I have a couple of questions, one for Phill and one for Cliff. First question for Phill is, if you have a physical process which exhibits discontinuity, how would the Bayesian approach handle that compared to other approaches? Because in the process you showed they're all continuous types. Here you have an explicit discontinuity,
Yes.
rather than implicit. But you can have processes where you have an implicit discontinuity, where phase change. And I think that the Bayesian approach may have struggled with detecting discontinuity because of the way it tries to fit the space. I'm just saying as an example where you have these discontinuous processes, how would a Bayesian approach handle it?
To be honest, I really wouldn't know until I see a specific example of how that works. Actually, what I would do is probably come and see you and discuss it. I mean, with this one, it was it is discontinuous. So there's a step change there, and we force the models to meet at that point.
Yeah.
I think the Bayesian way is to really try and understand the model of what the physical process is, and try and work that through. So I really can't answer your question.
Yeah.
Sorry.
Okay, no, that's fine. Another good question to Cliff. You presented a 14-dimensional parameter. You had 14 parameters, which you showed the model performance. But suppose one is interested in actually interpreting the actual parameters rather than the model's performance. When wouldn't the correlation structure then be important? So I wonder whether you actually determine the correlation structure of the parameter space.
Yes, but it's impossible to show it in presentation form because there are 14 dimensions. But yes, there is essentially a 14-dimensional parameter space, which is very much like a 2-dimensional parameter space being 14, if you can see what I mean. So this is 2-dimensional, but lots of whizzy lines over 14 dimensions. And yes, that all has to be calculated in order to work out what the maximum probability is. So that all exists in effectively matrix form.
Yeah, but there'll be some correlation between the parameters, which can cause some difficulties in interpretation.
Yes, but you can marginalise out a particular parameter against all the other parameters. But to extrapolate these things here, we use the full covariance matrix to sample from that to extend the models out. That makes any sense?
Yes, thanks.
Okay. More questions?
Not so hard.
I'd probably make it simpler. John Saltmarsh from Decontinuity. Where am I going with this question? So yes, the start would be good. Sorry, I completely lost my thread. Can you come back to me?
I will come back to you. Can we have another question? Please. David.
Does the analysis take into account that the performance of the early generation condensing boilers wasn't as good as the later generation?
Yeah, it doesn't assume any. Well, what it assumes is when do you mean the early generation?
Well, probably before 2005. That's the trouble.
Yeah, right. So in that case, it has no impact, really, or very limited impact because the penetration is so low. Now, we've produced an average efficiency and an average uplifting efficiency over the time period. So yes, it's in there, but when the penetration is incredibly low, it has a fairly small impact. As the performance of condensing boilers goes up, yes, that will slowly swing up.
John.
Okay, I think I can phrase my question a bit better now. Looking at the price side of things, you've obviously sort of worked out here the sensitivity as far as energy savings concerning the sort of boilers. But there was a big slope down, which was sort of driven predominantly by the price, or was it? Have you got a sort of sensitivity as far as the price is concerned?
Yes, we decided there were too many slides, and we've calculated what's effectively the price elasticity of gas use, water and space heating, and I think it's minus 0.3 plus or minus 1. So it's a reasonable price elasticity, and that's kind of in line with. It's a fairly broad range. It's in line with most of the estimates.
So would it be more effective to put up the price of gas a little bit rather than going with the policy of reducing boilers?
The question is always how much. Popularity of policies and things like that. Yeah, made the price go up by a factor of 10. It had a pretty profound impact on the gas use.
I just wondered whether a nautical analogy might be appropriate. On things like ships, you often have redundancy in the system. But I get the impression that we're moving to a situation where we try to remove redundancy from the policy environment we subject important things like housing to. And I just wonder why we do that. If it's really important to reduce carbon dioxide emissions from the housing stock, then perhaps we would accept that redundancy as you would think, because it means that even if one policy fails, then at least another one will kick in and do some good. Andrew.
Yeah, so Andrew has the Energy Technologies Institute. You give an example where you have a limited amount of data, some fairly simple models and 14 parameters. What would happen if you had the energy used for every single household for each of those causes as a root of data? Your Monte Carlo sampling would then have a rather large space to consider and lots of different things to fit. Would Bayesian simply become impractical because you had too much data? Or would in fact, I'm asking a very naive question, would in fact you go, no, fantastic?
Would be fantastic, but you would set up your models to extract the information you want from the data. So there's no point in setting up the models to model absolutely everything to do with behaviours. It depends what you want out of the system.
To be my supplementary, so your hypothesis about what's happening in the houses are now richer.
Yes.
There's lots of variables you're interested in you haven't measured. So you have a hypothesis where you have hidden variables.
Yes.
And you're having to guess why a particular household is doing something different than your model of households would say. How do you deal with that?
We can't talk about individual houses with this analysis. Is that what you're talking about?
If you had data on individual houses, how would you treat that in terms of your analysis?
Well, there are two ways. I mean, one thing is we could do a slightly different analysis per household and see what happens. And the answer is that lots of weird things happen in individual households, and we'll struggle to cope with that. But we'll probably come out. We've never tried it, but we're probably going to come out with some relationships in terms of temperature and price that look very vaguely like these, but on an individual house-by-house basis, these are going to be all over the place. And then you could work out different ways of aggregating. So it would allow us to aggregate in different ways. You'd hope that if you had data on the basis of individual households, you might have more metadata as well. And the more metadata that you've got, obviously, the more things that you can include in an analysis in terms of aggregating to a medium scale, national, or on an individual basis. Obviously, then you've got metadata. Simply, if you don't have adequate data, then your model doesn't fit. This isn't curable. Sometimes the model doesn't work. You have to have a model that is appropriate for the data you've got. Until we tried it, it's hard to know. But on an individual housing scale, it'd certainly be extremely variable age. Depends how many years you've got as well.
Okay.
Yeah, Mike Foster from Energy Utility Alliance, a trade association that includes all the UK boiler manufacturers. How does your data compare to, let's say, manufacturers' data or data available for, say, the Energy Savings Trust on the cost savings achieved from having a condensing boiler compared to a non-condensing boiler?
Well, we haven't calculated cost savings associated with individual boilers. And the closest we come to that is projecting the efficiency on the basis of condensing boilers. And so we see condensing boilers compared to conventional boilers. We see that's the gamma, the increase of efficiency associated with fitting as being 0.25 plus or minus 1.5, fairly big error bars in that. Definite improvement of efficiency, but our certainty in the savings associated with it are a little bit more loose than you like, but that's the data.
Can I just butt in here and say that what I think is interesting about this analysis is that instead of starting with measurements of individual efficiencies in individual dwellings, what Phill and Cliff have tried to do with this paper is to see if they can see the signal that switch to condensing boilers in the gas data. And what's so interesting about this is that you can. This is an example of top-down analysis, which in this particular case works nicely. Now, not all top-down analysis does work nicely, but this particular example does work nicely. And to my mind, it's been done in a particularly interesting and rigorous way, which I enjoy reading. Okay. Yes. I'm sorry, I can't remember everybody's name, but I'll take you next.
Yeah, Leonard DeMarco, and it's renewable energy consultant. The importance of this stuff is to inform policymakers, and it isn't clear to me how much information you're getting from this to inform policymakers about forming policy. You're making things more complicated, and not necessarily getting an answer which is going to help people like DEC in forming policy.
Well, I think our job is to do good quality research and analysis on the available data, and that people at DEC and so on are capable of understanding this kind of analysis in sufficient depth to appreciate what we're saying. Okay, it's complicated, but very rarely is the efficacy of policy analysed in numerical terms, it's quite difficult to work out when you introduce a new policy exactly what the impact of that policy is. As we can see, these are national data sets that are taken at length, and still we've got large error bands. I don't think that being able to give a lack of certainty should be any reason not to continue undertaking analysis. That would then be policy making in a vacuum. And then we can come to the conclusions, which are fairly clear. That condensing boilers, we're fairly sure, do make a significant improvement to the performance of the stock, and there is an
And you don't
increase
know why.
in efficiency. I do?
You don't know
We don't
why.
know
Well, no. That's
Well, hang on.
the nature of the analysis.
They use less energy.
Exactly.
Yeah.
See,
Well,
that's
this
the
is
priority, isn't it? That they use less energy. But
Well,
you don't know
ours-
whether it's
our
because
analysis
of price
is not-
increases or.
Well, no, ours has separated that out. That's the point. I mean, our analysis has separated price from efficiency from everything else. The purpose of our analysis is to separate all those factors.
So
So that is absolutely what we've done.
We didn't assume that condensing boilers used more. We didn't assume that gamma was positive or negative.
Yeah, exactly, and that's why I haven't been answering that question, is that we have not assumed that. We have not assumed an increase of efficiency associated with the condensing boiler. We've looked at the data and seen if the data reflects that, and it does. And that factor there excludes the impact of price. Price contributes to the error bars, but not to the figure.
Would it be possible for me to ask people from whom there are at least a couple of John?
I was just going to
do you
come
find
in.
this useful?
I was just going to come in and comment on this. This is the first time that I've seen this sort of this downward curve actually being sort of broken out into how much was contribution from temperature, how much was contribution from price, how much was contribution from the boiler processes themselves. So I don't think this has been done before. For that very reason, it's really useful because it does allow us to evaluate our policies and actually demonstrate that it's really delivering something.
Thank you. Okay, I'll take you next.
Chris Gordon-Smith, independent researcher. I just wanted to come back on the point over here about, which I think your point was, if you've got price controls, why do you need to regulate about boilers? What do you say? People must have condensing boilers. My understanding of this is that people aren't necessarily sort of rational agents in an efficient market. So some people, whatever the price, will carry on running inefficient boilers. That's my understanding. And therefore that's why you bring in regulations like that.
Okay. I'm going to take a chat at the back.
Thanks. William Burns, UCL-Energy Research Centre. I'm sorry I missed the beginning of the talk, but coming in at the end, what do you think is the next step in your research? What's the next critical question? Can you answer that?
I don't want to give too much away. I mean, we can apply this to all sorts of different policies that might be applied. The big advantage here was that we had a regulation change. So we've been asked previously, can you apply this to the uptake of insulation, things with that. The problem with that is it's actually really difficult. It happens over a kind of 30 or 40 year period, really slowly. Loads of other stuff happens during that time period. The chances of picking up a clear trend are therefore relatively low. But we can look at other policies where there's kind of clear data, and particularly here a set date that we can look at. One of the things that we're mainly focusing on is physics, and therefore we're mainly focusing on answering this question, really. Trying to understand walls.
Could
Could you apply this to check whether or not people who work in places where there used to be public smoking and now there isn't, because that's a fixed date, has there been an improvement in health, less cancer risk or whatever?
I think that's a question for
Actually, this has been done. And they looked at, but not this sort of analysis. That there is a more statistical approach, not a Bayesian approach, looking at what they call interrupted time series, where you have a time series and then you have an event, and then you compare before and after, and this has been done, but it's a different approach than this. And it's not done in a Bayesian, and it's purely empirical approach, while here it is physics-based. you start with the equation governing the processes, and you estimate the parameters there. There are so much fundamental relationships as risk, health risk coefficients, but it has been done.
But to answer your question, yes, we could do it Bayesian analysis in a very similar way if we had a set data.
I think we've got a question over here.
Well, my name is Harvey Beck from Loughton. I think the point has been picked up a little bit in terms of insulation. I was just interested in things like Phill, which the energy company obligation, which has pushed quite a lot of money into insulation measures. We're saying that perhaps it's difficult because there's a lot of other changes, but it may be interesting to pursue some new policy changes like that.
Yeah, in principle, yes. It totally depends on the quality of the data set, and that's our limiter.
Peter Raynham, Institute for Environmental Design and Engineering. I think it's only been that for a couple of weeks. Question, in your analysis you show that as gas price rises you drive down the balance temperature. So implicit in this, that as price rises we sacrifice thermal comfort. So when we put in an efficient boiler, do we then raise that balance point because we can achieve what we're doing for the same amount of money?
We might do, and that's something for a much more detailed analysis, a survey using mixed methods where you're combining monitored data with temperature data and some social sciences running alongside it.
Can I just make an observation? The price signal is over this period is of more of a factor of 2 or something.
Yeah, it's really big.
And the boiler efficiency signal is of the order of a factor of 1.1. So my guess is that the price signal will dominate in that particular case. In other words, everything that looks a bit like a price signal probably is a price signal, and probably isn't a consequence of the boiler signal.
So it's a 10% efficiency gain that you're looking at?
Yes, it's roughly, you take your starting efficiency, you multiply it roughly by, what was it? About 1.2. About 1.2. What was your
Yeah, 1.2.
Yeah. Okay,
but thinking if you applied this out to other potential savings like domestic installation, are you likely to see a change in the comfort threshold rather than the energy saving?
Like a comment on that, you're going to have a strong distribution effect. So the outcome for the population as a whole will be terribly dependent on the dominant behaviours of quite a small subsection of the population. So if you look at the feedback to eco, for example, people who have an eco observe very strongly that their house is more comfortable. If you ask them how much their energy bill is less, they will baffle. Something about which suggests they probably spend the same amount on energy, but they get more comfort for it. If you look at high disposable economic houses, the impact that price savings have on them or efficiency savings is complex. So they can form their own capital to invest in savings and they evaluate them in a different way.
Sure.
Hi, I'm Sue Wolf. I'm a technical manager at London Borough Haringey. I'm dealing with results of citizens to inspect their houses. So I was quite interested in the earlier section on the heat flux through a wall, because so I'm interested in the bricks rather than the policy, and particularly you left what you showed is obviously how important thermal capacity is in explaining heat flux through, but not enough. And I think you left the last slide showing actually that the heat flux in October, there was negative heat, but in actuality there's negative heat flux through that wall, whereas the model only shows positive heat flux. And I think that's quite an important observation to make, because it may be, I mean, and as I understand it, the value of what you're doing here is actually isolating out the important parameters to use in a model and testing them against their ability to predict over limited data ranges. And I've always found even simulation models actually just as rubbish as steady-state models, with a hugely appalling record of reliability. And actually also the models actually often have completely different physical bases. So I think it would be very useful to sort of develop that to see what is more appropriate. Because we're finding that all the the actual the measured u-value of walls is considerably different to the predicted one, and all of the models I've ever seen completely underestimate cooling loads in offices, and that really definitely needs to be dealt with. So something like that help the environmental designers actually produce more decent models.
Response?
I agree. But this is, remember, this is the heat going into the wall from the outside. It doesn't necessarily go all the way through.
It doesn't go through, yeah, there's this.
There's a thermal mass. But if you notice from the movie, notice this is in July. We are getting heat coming into the room from the wall in July as measured. Virginia here is going to study why exactly this happens, trying to model that using these techniques.
I noticed that people have just started to drift away, a little bit like the heat diffusing out of your wall here. So I'm going to take 2 or 3 more questions, and then we'll break and head upstairs for unstructured conversation. So, any more questions? Do we have any more questions?
You're just tempting people.
What have I said? Okay. Well, in that case, I would like to bring these proceedings to a close. I enjoyed the presentations very much, and I hope that you did. So perhaps if we could put our hands together and congratulate the two.